Hello, everyone. My name is Dimitri. I'm a third-year PhD student in chemical engineering at the University of Connecticut, and I'm one of the current developers of EAGO. So what is EAGO? EAGO stands for Easy Advanced Global Optimization, and it's an open-source deterministic global optimizer for non-convex MINLPs, and it's written entirely in Julia. EAGO is a fast general solver, but it's also a research platform that allows users to modify essentially anything that EAGO does. So any function we have written, a user can change it to do something else if they'd like. For example, EAGO uses McCormick relaxations for the lower bounding routine, but a user could substitute in their own lower bounding routine without impacting the rest of the functionality of EAGO. We have some documentation and notebooks on this if you're interested in trying it out. Some use cases of EAGO in my lab would be semi-infinite programming, dynamic optimization problems, and other advanced formulations that contain complex user-defined functions. And EAGO is able to handle all this because we interact with JuMP, and one of the main things I'm going to talk about today is how JuMP's development has impacted the development of EAGO. So to start, I'm going to go through an example pretty quickly. It's just a kinetic parameter estimation example where you want to, it's pretty common in chemical engineering. I guess it might not apply to most people here, but the objective is to minimize the sum of squared errors between some calculated model and experimental data. In this case, the model is based, or the data we have is based on an intensity of light through the solution. So we want to minimize the sum of squared errors to calculate the unknown kinetic parameters. And we're given a system of ODEs based on kinetics. We can, derive our equations. And there are a few different ways you can solve this, but what we're going to do is we're going to take the concentration. We're going to use that to we're going to use the differential equations to calculate the concentration, to then calculate intensity, and then minimize the sum of squared errors with the experimental data. So there are a few different ways you could solve optimization problems with differential equations. In this case, I'm just going to use explicit Euler and turn the differential equations into a system of algebraic equations. So you could use these as constraints, or you can just iterate through them in the objective. If you had them as constraints, it depends on how many time steps you have, but if you had 200 time steps, you would have 1,000 constraints. But in this case, I'm just going to iterate through in the objective function. So here's what the code might look like. It's missing some stuff just to make it smaller. But basically, once you load in all of your data, you can define functions to calculate concentration, intensity, and then the sum of squared errors. That's what the objective function is. And then you can make your JuMP model with EAGO as the optimizer. In this case, we're using Groby as a subsolver. And after this, you define your parameters. You have to register your function through JuMP, and then you set that as your objective function. And no matter what the function is, as long as you can register it through JuMP, EAGO is able to optimize it by constructing McCormick relaxations and find a global solution or determine if it's infeasible. So this is only possible because you registered the model in JuMP. If you can't do that, then EAGO can't really do anything with it. So that's just an example to illustrate that EAGO can handle complicated user-defined functions. Okay. So how does EAGO use JuMP, I guess? So JuMP's really great because it provides a good user experience, but as a solver, we need to be able to interpret the way that JuMP stores the model and then transform the information to use our specialized routines. So the model goes into JuMP, and EAGO will just send basically the exact same version of the model to IPOpt to generate an upper bound. You can use any other NLP solver if you'd like. Then the problem is relaxed through another package we have, McCormick.jl, and we send it to an LP solver or an MILP solver, depending on the type of problem you're solving. And that's how we get a lower bound of the problem. So by default, EAGO uses IPOpt and CBC, but we set it up in a way so that you can use any subsolver you want, as long as it applies properly and it's compatible with JuMP. So if you want to use GLPK instead of CBC, you can just change a simple thing in the subsolver block of EAGO. And because we rely on JuMP for features like this, our development is closely tied to what JuMP does. So here's a timeline kind of illustrating what EAGO has gone through. So at the start, EAGO was developed by a graduate student named Matt Wilhelm, who recently graduated. But he attended JuMP Dev that same year. He's in that picture you probably can't see. So that same year he presented on it. I don't think he's been back since. But after that, the following year, JuMP switched from using McCormick-based to math-opt interface, and then EAGO had to do the same thing a few months later. And over the next few years, Matt continued working on EAGO, like adding new features, improving the performance, and in early 2022, he released a version that changed the way we handle nonlinear expressions. So previously we would use Weingart tapes, and now we use a directed acyclic graph that's really similar to the way MOI handles their expressions. And shortly after that, JuMP reorganized all of their nonlinear content into a new submodule in MOI, but Matt was kind of busy getting ready to defend his PhD, so he didn't really prioritize updating EAGO again. But it's still important for the rest of us to update EAGO because we don't want people to have to use an old version of JuMP in order to use EAGO. We want everyone to be able to use the latest packages so they can use whatever they want for the rest of whatever they're doing. So when I joined the lab last 2 Januaries ago, I guess, the first thing I did is I converted all of the old nonlinear stuff to the new nonlinear stuff. And currently I do stuff like updating the documentation, fix any bugs. But one thing I missed as I was doing this update is that JuMP released a new way to handle nonlinear expressions. So these 2 features that I mentioned in JuMP are kind of the main things I'm going to talk about, mainly the last one. So the first one is the nonlinear refactor. This was pretty straightforward. They just moved everything from JuMP.derivatives to MOI.nonlinear, and before it was completely undocumented, but now it's very well documented. I probably read more of it than anyone else. It was pretty straightforward, just change the names, update the operator registry a little bit. And here's just an example, like you just change a simple name, and that was kind of a lot of what that was. The second change is a lot bigger. That's kind of what I'm working on right now. It's dealing with how EAGO handles nonlinear expressions and user-defined functions. So as of 0.7, EAGO creates a directed acyclic graph, which kind of mirrors what MOI creates, and we use this for constraint propagation, forward pass to construct our relaxations and other things. So here's an example of comparing what MOI stores and what EAGO stores. So this is sine of x squared plus x. You can see they're very similar. Matt kind of got inspired by MOI to kind of just replicate what they have and add a few things. So the differences here are the operator registry, and JuMP stores the parent information, but EAGO stores the children information. And yeah, so we convert the operator registry so that EAGO can construct our relaxations through McCormick. That's pretty important. And then I'm not sure why Matt chose to store the children instead of the parents, so maybe that can be looked at in the future. But basically all of Matt's work and the current version of EAGO assume that the expressions are in these 2 forms. You take it from MOI and you put it in that form. So when you introduce this new way of handling nonlinear expressions, I guess I should back up a little bit. So this is when JuMP went from using @NL constraint to @constraint. So anything that is a nonlinear constraint in JuMP will end up being an MOI scalar nonlinear function. And this is a symbolic tree. It's no longer using that first code block. So how do we go from something like this back to what EAGO needs? And this is pretty difficult for us to develop because I'm not the original developer. I kind of just joined. So I kind of see it as 2 options. I can either rewrite all of EAGO to account for this change and forget about the old nonlinear stuff, or I can just maybe find a way to convert this new symbolic tree into what EAGO uses now. So currently that's what I'm working on, just converting the symbolic tree into a node tree, because it doesn't seem like they're planning on deprecating the nonlinear stuff, so we'll see. So yeah, moving forward, we plan to have support for scalar nonlinear functions, so it'll improve the user experience because they can just do @constraint instead of @NL constraint and get really specific for their problems. But aside from that, we also want to update EAGO's use of JuMP for our other advanced problem formulations like semi-infinite programs and implicit functions. I'll just quickly touch on semi-infinite programs here. You heard about this yesterday, but basically you have a bi-level optimization program. You can reformulate it into a single optimization problem and apply a specific algorithm to still get the solution to the original problem. That's pretty important for chemical engineers, or engineers, I guess, solving worst-case design problems. Anyway, solving this in EAGO, you have to define all your functions separately as Julia functions, and then you call this function in EAGO, which applies the semi-infinite algorithm. And internally, it registers and creates JuMP models. But what we really want is for users to be able to just create a JuMP model, say they're solving an SIP, and then it'll still do the same routines that it needs to. So these are the things we're working on moving forward. Hopefully it wasn't too confusing. Yeah, you should try out EAGO. Let me know if you have any problems. So my acknowledgements, I would like to thank my lab and JuMP community for letting me present here. And one final thing, if you're going to ISMP, check out Robert's presentation on GPU-accelerated deterministic global optimization, which uses EAGO as a backbone. Thank you.